Welcome back to the deep dive. Today we are peering inside, well, the 3-pound universe that's sitting right between your ears. The human brain.
And we are diving into a concept called neuroplasticity.
It might just be the single most hopeful and, frankly, radical idea in all of modern neuroscience.
It really is. It fundamentally changes how we view, human potential. Neuroplasticity is the brain's remarkable ability for its neural networks to change, to grow, and reorganize.
So it's literally rewiring itself.
Exactly. It's the brain's power to change its own connections, adapting its structure, its function, all in response to new information or the environment or even physical injury.
And what's just astonishing to me, especially when you look back, is that for centuries, the prevailing wisdom, the absolute dogma, was that the brain was, well, fixed. That after maybe early childhood, it was a finished machine. Once the wiring was set, that was it.
No upgrades, no repairs. And that rigid belief, it really dominated the field for far too long.
Right.
For much of the 20th century, scientists just operated under this assumption that the adult brain structure was static. You were basically stuck with what you had.
And it took some pretty groundbreaking research to finally shift that.
Oh, absolutely. It was mainly in the later half of the century that we got conclusive proof showing the brain exhibits this profound plasticity well into advanced age. The developing brain is definitely more plastic, but the adult brain, it's dynamic, it's adaptable, and it is constantly evolving.
So our mission today is to deep dive into this revolution in thought. We'll trace the history of the idea, we'll break down the specific ways the brain changes, from strengthening synapses to moving entire functions around.
And we'll look at some of the most dramatic, real-world examples of how stimuli, whether that's intense learning or injury or even mental health treatments, can physically rewrite our neural landscape.
Let's start at the beginning then. How is such a fundamental idea ever missed? It's just incredible to think that such a core property of our biology was essentially, overlooked or even rejected for so long.
Yeah.
Where did the first sparks of this plastic brain idea even come from?
Well, the term plasticity itself was first used for behavior, not the brain.
Oh, really?
Yeah, way back in 1890. The philosopher William James, in the Principles of Psychology, he described it as a structure being weak enough to yield to an influence, but strong enough not to yield all at once.
That's a great definition. It's about lasting change.
It's a very elegant way to put it. The specific term neuroplasticity came later from a Polish neuroscientist named Jerzy Konorski.
But I remember reading that the core idea was floating around even earlier than that. There's some story about early evidence that was just completely forgotten.
That's right, you have to go all the way back to 1793. An Italian anatomist, Michele Vincenzo Malacarne, he did some of the first experiments showing actual structural change. He took pairs of animals, trained one group really extensively, and just left the other group alone.
And what did he find?
When he looked at their brains, he found the cerebellums, the part for coordination of the trained animals, were substantially larger.
That's structural evidence, 2 centuries before it was accepted.
Exactly. It's kind of a tragedy of science, a groundbreaking discovery just buried by the scientific consensus of the time.
So why did that consensus that the adult brain was fixed, why did it hold on so tight?
Well, it was partly just the difficulty of actually observing the changes and also the influential theories of the era. I mean,
Well,
even though Santiago Ramon y Cajal, the father of modern neuroscience, even he used the term to describe changes in adult brains.
his contemporaries just didn't run with it.
They focused more on what they could see, which was changes in the peripheral nervous system. The central nervous system just looked static to them. It really took hard, undeniable evidence in the lab to force a change in thinking.
Okay, so what was that evidence? What was the research that finally pushed the field past that dogma?
I'd say there were 2 major shifts. The first was in 1964. Marion Diamond produced the first solid scientific evidence of anatomical brain plasticity.
How'd she do that?
She studied rats. She had one group in these enriched environments with toys and other rats to play with, and another group in isolated cages. And she found the rats in the fun cages had thicker cerebral cortices.
So the environment itself was physically changing the brain.
It was. And then the one that really caught the public's imagination was the London taxi driver study.
Ah, yes. Led by Eleanor Maguire. This is such a fascinating one.
It's a classic
Yeah.
because it showed that a specific, really intense cognitive task had to change the brain. To get a license, these drivers have to learn the knowledge.
Which is just an insane amount of information. 25,000 streets.
25,000 streets, landmarks, routes. It's one of the toughest navigation tests in the world. And the study found significant observable structural changes, specifically in their posterior hippocampus.
The hippocampus being the brain center for spatial memory.
That's the one. They found a redistribution of gray matter. The posterior part, which handles spatial stuff, was significantly larger in the taxi drivers.
And it correlated with how long they had been on the job, right?
It did. The longer they'd been a driver, the bigger the structural change. So acquiring all that information didn't just get stored somewhere. It literally demanded a physical restructuring of their brains. That really cemented the idea. So if we dive into the mechanics of how this works, I should say there's no single all-inclusive theory, but we generally categorize the changes into two main types, structural and functional.
Okay, let's start with structural. If the taxi drivers were gaining gray matter, that sounds like the actual hardware is changing. How does that happen? Is the brain growing new cells?
That's a great question. So structural neuroplasticity is all about changes to the brain's anatomical organization and its neuronal connections.
Good.
We measure it by seeing, increases in gray matter or changes in how dense the connections are. And while new cells are produced, that's called neurogenesis, it's important to be clear, large-scale adult neurogenesis in humans. Well, it hasn't really been convincingly demonstrated outside of very specific areas, like the hippocampus.
I see. So it's less about building a whole new factory and more about renovating and upgrading the existing one.
That's a perfect analogy. It's about optimizing the existing networks by strengthening them, pruning away what's not needed, and just reorganizing.
Okay, so if structural is the physical architecture, then functional plasticity must be the operational side, the software. And that seems like it would be key for recovery after an injury.
It is absolutely key. Functional neuroplasticity is the brain's ability to alter the functional properties of its networks. This is where the real magic happens during recovery.
Because it lets you move jobs around.
Precisely. It allows functions to transfer from a damaged part of the brain over to an undamaged, healthy part. It's the brain's ultimate insurance policy.
So how does the brain decide where to move the function? Are there different strategies it uses?
It has several. One we see a lot, especially in kids, is called homologous area adaptation.
Okay.
If an area for, say, language processing gets damaged in the left hemisphere, the corresponding area in the right hemisphere might just take over that job.
It shifts the workload across the midline.
Exactly. Then there's the one we saw with the taxi drivers, map expansion.
Right. More practice means more brain real estate.
The more you practice an instrument or memorize routes, the more neural territory gets dedicated to that skill.
But what happens if the brain loses an entire input signal, like with sensory loss?
That leads to something truly dramatic called cross-model reassignment. This is where a brain region that's been stripped of its normal input, say the visual cortex in someone who is blind, starts receiving and processing signals from a totally different sense, like touch or hearing.
The hardware gets completely repurposed.
Completely. And then there's one last one, more complex strategy called compensatory masquerade.
That sounds intriguing.
This is when, after a minor impairment, instead of fixing the old pathway, the brain just develops entirely different cognitive strategies to perform the same task. It's a workaround.
Relying on different mental tools to get the same result.
You got it. And all of it, boils down to the cellular level to synaptic plasticity.
The connections between the neurons themselves.
Right. It's about strengthening or weakening those connections, the synapses. We talk about long-term potentiation, or LTP, which strengthens connections for learning and memory.
And I'm guessing there's an opposite.
Yep. Long-term depression, or LTD, which weakens them. It's how we clear out old, unused information. They work together, constantly tuning the network.
So let's move from the mechanics to the real world. The most obvious application here is recovery from brain injury. I mean, neuroplasticity is the entire scientific basis for things like stroke rehabilitation.
It is. Every single effective rehab technique we have, like constraint-induced movement therapy, where you force a patient to use their impaired limb.
You're basically forcing the brain to find a new way.
You're forcing it to create new functional pathways. You're actively driving that cortical reorganization.
But you mentioned before that there's a dark side to this, that sometimes the rewiring goes wrong. This is maladaptive plasticity.
Yes. The most common and painful example is the phantom limb phenomenon.
Right, where someone feels pain in a limb that isn't there anymore.
And it affects a huge number of amputees, 60 to 80%. The sensation, the pain, it's directly linked to cortical remapping. The area of the cortex that used to map to the missing limb is now silent.
And other areas move in.
Nearby representations, maybe from the face or the upper arm, they invade that silent territory. So when the face is touched, the brain might interpret that signal as coming from the missing hand.
And that causes the pain.
Well, what's crucial is the research from people like Herta Floor. She showed that this major remapping really only happens in patients who suffer from phantom pain, not just the sensation. The brain's attempt to make sense of missing input can, unfortunately, end up creating these debilitating chronic pain signals.
And this isn't just limited to amputation, is it?
No, not at all. We see it in chronic pain conditions like complex regional pain syndrome or even chronic low back pain. Studies show there's a diminished cortical representation of the painful area, even a reduction in gray matter volume.
But the good news is that those changes can be reversed.
That's the hopeful part. Successful treatment often resolves those abnormalities. It shows how dynamic the system is, for better or worse.
So let's switch back to a positive example of extreme change. Sensory compensation. What happens when someone is, say, deaf or blind, and the brain has to completely repurpose huge chunks of its cortex?
This is cross-model reassignment on a massive scale. In people who are deaf, their auditory cortex, the part normally for sound, is often repurposed for enhanced peripheral vision and touch.
So they might be more sensitive to vibrations.
Significantly more sensitive because the brain has reallocated those resources. The hardware gets rerouted to boost other senses.
And in blindness, it's even more remarkable.
It is. Blind individuals who learn to use echolocation, making clicks and interpreting the echoes to navigate.
Like a bat.
A bit like that, yes. They process those sound echoes in the parts of their brain normally used for vision.
So their visual cortex learns to see with sound.
That's a perfect way to put it. It's an absolute demonstration of functional cross-model reassignment.
So if the brain can fundamentally rewrite itself after something catastrophic, what does that mean for our day-to-day conscious efforts? How much power do we have to intentionally drive these changes?
A tremendous amount. Our lifestyle choices and conscious efforts are powerful plastic drivers. Take multilingualism.
Learning another language.
Studies consistently show that bilingual people have significantly greater gray matter density in the inferior parietal cortex than monolinguals.
So it's a measurable physical change.
A measurable change. They also have increased myelination in the white matter tracts, which suggests faster, more efficient connectivity between brain regions. You need that to switch between languages quickly.
So learning a language is literally a structural workout for the brain. What about things like meditation?
Same principle. Long-term meditation is linked to increased cortical thickness and more gray matter in regions tied to attention, self-awareness, and emotional control.
Areas that process fear and anxiety.
Exactly. The practice physically reinforces those networks. It's the same with long-term artistic training, like playing music. It can macroscopically imprint a neural network, making that activity easier and more automatic over time.
Okay, and we always hear that exercise is good for the brain. Is there a specific neuroplastic mechanism behind that?
There absolutely is. Aerobic exercise is basically a chemical promoter for neuroplasticity. When you exercise, you increase the production of growth factors, especially one called brain-derived neurotrophic factor, or BDNF.
BDNF.
Think of it as high-grade fertilizer for your brain. It promotes the survival and growth of new neurons.
So more exercise, more fertilizer.
And that leads to measurable improvements in executive function and increased gray matter volume, especially in the prefrontal cortex and, surprise, surprise, the hippocampus, the same area the taxi drivers changed.
Let's talk about the newest frontier here, using this knowledge to treat mental health disorders like depression.
This is a really major breakthrough. We've established a clear inverse relationship. The lower the synaptic density, the more severe the depression. The problem with traditional antidepressants is that they're slow.
Right, they could take weeks or months to work.
Because they're only slowly improving neuroplasticity. But the new treatments are showing rapid, almost immediate structural results.
How are they doing that?
Researchers have identified a new class of compounds they're calling psychoplastogens. This group includes things like ketamine and certain serotonergic psychedelics.
And what makes them different?
They bypass the slow, generalized pathways of the old drugs. They rapidly promote neuroplasticity, causing a massive, fast increase in the number of dendritic spines, the connection points on neurons. They literally rebuild the connections that were lost to chronic stress or depression.
Offering faster and hopefully more enduring therapeutic effects.
That's the goal. It's a very exciting area of research. Hashtag tag outro. Go.
We have covered a staggering amount of ground today.
Yeah.
From the historical fight to even accept the idea of a plastic brain through Malakarn's forgotten discovery in the London taxi drivers.
All the way to the mechanics of functional adaptation and these profound applications in recovery and mental health.
And the core message really seems clear. Your brain is a dynamic, living system that is always, always reacting.
And what really stands out in the latest research is this crucial link between plasticity and aging. There's new data, transcriptional profiling, that shows the expression of genes that are central to synaptic plasticity. Well, it starts to reduce after age 40.
Oh.
And that reduction speeds up significantly after 70. And this happens alongside a marked increase in cortical DNA damage.
So what's the question that raises for you?
It raises a critical question for all of us. What consistent, sustained level of engagement, physical, mental, social, is actively required to counteract these biological trends and maintain a plastic adaptive brain deep into old age? The bar might be higher than we think.
So what does this all mean for you listening? The dynamic nature of your brain really confirms that consistent learning, regular exercise, intense mental engagement, they aren't just hobbies or desirable habits.
They're fundamental biological necessities.
They're your ongoing maintenance schedule. The fact that your brain never truly stops changing is the most powerful takeaway of all. If you want to change your mind, literally, start finding your next great rewiring project.